Hi, my name's Nick, and today I'll be talking about Bayesian networks, which was a topic introduced to me in my class in Artificial Intelligence, which is CS440 or also EC448, and it's also a topic that comes up in CS598, which is graphical models. So to start off, what are Bayesian networks? They were something pioneered by Judea Pearl, who advocated for a probabilistic approach to artificial intelligence, and they're a way to represent a full joint distribution more compactly by taking advantage of conditional probability distributions. And really, they represent complex probabilistic systems that can be represented with a directed acyclic graph. So I'll talk a bit about the structure of the graph so that you have an idea more of what it's representing. So each of the nodes in the graph represent random variables which can be discrete or continuous valued. And then the arcs or edges represent interactions and the influence of one variable on others. So for this graph, this was the burglary network introduced by Judea Pearl. So we have these 5 random variables, which are each binary, as in really the only possible values are they happened or they didn't happen. So this scenario is basically we have a house with an alarm. We have some level of burglary in our neighborhood and also earthquakes occurring. The alarm is meant to alert you to whether burglary is happening in your home, but it might be triggered by an earthquake. And then you have 2 neighbors, John and Mary, who might call you if they hear your alarm going off. So really, this is saying that the burglary could affect the alarm, the earthquake could too, but the burglary and earthquake aren't related to each other. And then John could call and Mary could call, and whether or not they call is conditionally independent given a specific value of the alarm. So one key property of these graphs is that each node is conditionally independent of its non-descendant given its parents, which gives us what's called the chain rule of probability. So the joint distribution of several random variables is equal to the product of the conditional probabilities of each random variable given its parents. And then something else of importance to specify is the model parameters. And this is where we can really see the advantages of a Bayesian network. So if we wanted to store a table of the joint probability distribution for this network, we would need 31 rows in that table or 31 parameters, which is a lot because the number of parameters, it would be exponential in the number of variables because this has 2 possible values, this has 2 possible values, and so on. So we would need 2 to the 5th specific joint representations. We don't need to save the last one though because the value of the last one is just 1 minus the sum of the rest. So we would require around 31 parameters. But using the BaseNet, we would need a lot less. So for this example, we would need 10 independent parameters, which would be about a 70% reduction. And I have this formula here to give you the number of parameters for a variable that has parents. So D is the set of domain values for a particular random variable. So the number of parameters for a specific variable would be the cardinality of its domain minus 1 multiplied by the sum of the cardinalities of all its parents. So basically, as an example, an alarm can take 2 values. All these can take 2 values since they're binary valued. So this would be 2 minus 1. And then burglary and earthquake can both take 2 values, i.e. they happened or they didn't happen, which would lead to 4 combinations. So we would have 2 minus 1 times 2 plus 2, which gives us the 4 parameters we would need as seen here. if it doesn't have any parents, we just need one parameter for each value it could take on, -1. So for a binary variable with no parents like burglary, it either happened or it didn't happen, so we only need the probability to store the probability that it happened, because the probability it didn't happen would be 1 minus that. And that same logic applies everywhere else, so the probability and the alarm didn't go off, given that the burglary and earthquake happened, would be 1 minus 0.95, and so on. So for making inferences in a Bayesian network, something we can always do is find the joint distribution of the evidence and query variables, including any variables that are dependent on those, using the chain rule. So for this example, here I use the uppercase letter to denote the random variable and the lowercase letter to denote a particular value that that random variable can take on. And since these are binary, this would be like 0 or 1, or true or false. So the probability of John taking on some value is dependent on the alarm, and then same with Mary by the chain rule, as we can see that alarm is a parent of both of them. And then we would also multiply by the probability of the alarm taking on a certain value, given the burglary and earthquake taking on certain values, which would be given by this table. And then burglary and earthquake have no parents, so we would multiply just the probability of either of those occurring. Then we could marginalize over the irrelevant variables, and then renormalizing using the definition of conditional probability as necessary. This step isn't always necessary. For example, in the naive Bayes classification task, we're just finding the argmax, some probability of a class given evidence, and so in the denominator we would just have the probability of observing that evidence, which isn't needed since it'd be the same for every class. So let's say we want to know the probability of a burglary occurring in our house, given that both John and Mary called. So by the definition of conditional probability, that would be probability of burglary happening and John calling and Mary calling divided by the probability of John calling and Mary calling, which can both be found by marginalizing over the joint distributions. So for all these uppercase random variables, that's the probability of them actually occurring, and these are the probability of alarm and earthquake taking on whatever values. So if we sum up over all those possible values, we get the probability of John calling, Mary calling, and the burglary occurring. And to find the probability of John calling and Mary calling, we would sum up over the possible values of the burglary occurring or not, alarm, and earthquake. And that's how we could derive that probability. And then for learning Bayesian networks, there's two types of learning we could discuss. One is parameter learning. So if you have fully observed data, you can use maximum likelihood estimation. And basically what MLE is just finding parameters that make the observed data most likely. And then if there's partially observed data, or you have hidden variables, you would use something called expectation maximization, which basically you randomize the parameters, use those to find expected counts, use those expected counts to find the probabilities, and use that to re-estimate parameters, and you can keep iterating until convergence. The reason why you might have hidden variables is it would make the structure of a Bayesian network less complex in certain cases. And then for actually figuring out the structure of a Bayesian network, one approach is knowledge engineering, where you try to emulate the judgment of a human expert with domain knowledge. So for creating a Bayesian network for diagnosing a disease, we might ask a doctor probability of having a disease, what kind of factors could affect that, what kind of symptoms we might observe, what other diseases might affect those symptoms, and so on. And then there's also causal analysis, which is basically trying out different orderings of the graph and seeing which one captures the probability distribution most closely and has the lowest number of edges. And these examples were taken by the textbook used for CS440, which is Artificial Intelligence, a Modern Approach. In that textbook, you can see explanations more in depth of Bayesian networks and also applications in several fields, such as natural language processing, for example, or classification. And that's it. Thank you.